All right. Back at work in the early morning hours. And we've got SPIRiT working. We did that last time. The question is what to do next. And I think what we're going to do is alter the optimization problem. That's right. We're going to minimize over k now. But we're going to impose a constraint subject to, let's see, so the L2 norm of dk minus d is the set of sample indices. Right, okay, so dk minus k collected less than or equal to an epsilon. And so what's going on here? So we know that the values of the k collected, the values of k space that we collected are not perfect, right? There was noise in those values. And so if we know a bound on noise, which we can estimate, a couple different ways to estimate this, then we will be able to, well, the feasible set will be larger, so we should be able to get a smaller value of the objective function, this objective function that I've highlighted here, while still remaining within the noise of the collected values, and that's physically feasible, right? Like that's right. Not right, but that's, realistic. Okay. So then, first things first, let's add a parameter epsilon. It's got to be non-negative. Okay, now, I'm hoping we don't have to change any of this. We're going to have to add some stuff. I'm hoping we don't have to change any of it. Right? I don't think we have to change apply A. Because it's just W minus I. Well, it's this. The objective function is the same, right? So I don't think we have to change apply A. I don't think we have to change B. We are going to have to change, we're going to have to add some more stuff. I'll show you what that is in a second. And we're going to have to use a different solver. Because the question is, how are we going to handle this constraint, right? Oh, no, 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 no. We are going to have to change stuff. Because the optimization variable is different. Okay. You see, apply A right now takes in a sample mask. It fills in the data. All right. Before we do this epsilon thing, let's see if we could just make SPIRiT a little more efficient. Running this, whatever it is, (10.3 seconds). Okay. All right. Pad data is taking a lot of time, 2 seconds. That's not surprising. Where is that? Insert conv2. I'm slightly confused. This is certconv2. So what is this? Oh, this is pad data. Okay, this is the function pad data. Yeah, okay. I get it. Padding data is expensive. You have to allocate memory and then copy values. Great. The FFTs are taking time. That's not surprising. FFT shifts are taking time. Now here's an interesting question. Does it matter? Do I need these FFT shifts? That joint test fails. Yes, I do. Right, because when you're testing the adjoint, you need to know the location of the origin in the circular, when you're implementing the adjoint, because the origin is where it flips about. Okay. And flip dims flips about the center. So we could implement a circular convolution that has the origin in the first element. And then if you want to do the origin in the center, you have to do these shifts. And then that would be more efficient in some circumstances, but it's not what I'm worried about right now. All right, so the one way I thought we can maybe make SPIRiT more efficient in an interesting way is apply A. You see that apply A does this apply W and then minus, right? Because it's doing W minus I. Where's apply W? But we could just implement, as we discussed before, minus I. We can implement directly W minus I. And what would be the difference? Instead of padding with the 0 right here, we pad with the minus 1. So this was done in the original code released with the SPIRiT paper. All right, so then what? So W is now actually not W, but W minus I. So where does W get created? Why does it get created way up there? Because these functions use it, or at least apply W uses it. Okay. We don't, I mean, because of the way MATLAB works, this is a function defined within a function and a scope to all of the variables outside of it. So we don't need W to be defined before it, but I just tend to do that. Okay. So we've replaced this with minus 1. So now this W becomes actually W minus I. And so apply W becomes apply W minus I. And so we no longer need this subtraction. So that's what I was thinking of. This is 66, MRI Recon Spirit. Where's the profile? Line 66 of MRI Recon Spirit. Takes a tiny amount of time. This is what I'm talking about changing right now. Well, I'm not sure that's worth it. Where is it? It's 66. It does, I mean, it's more than 0 time, but not much more. I guess also 73 and 76. Where are they? Okay, so since it's in the iteration, maybe it will actually take some time. MRI Recon Spirit. Where's apply W? Here. Nope, it takes very little time. The circular convolution takes a while. This is apply W minus I. But wait, I'm confused. So this shouldn't be minus I. The profiler is like updating based on the changes to the code that I've made. Oh, I took out the, wait, what? All right, so this is minus, this used to be, this is apply W minus I. What's going on? Apply W minus I used to have stuff here. Oh, it was in apply A though. Okay. Where is apply A? This file was modified during or after profiling, so you can't see the listing anymore. Let's just profile it again. Okay. Apply A takes some time, but very little of it is self-time. 73. Okay, so this is taking 4 seconds, and this is taking 5. And I'll bet you that we can make that ever so slightly smaller. If we get rid of the subtraction. I like efficiency, so let's do that. At least we'll have done something today. Apply W minus I. Oh. Okay. I'm never sure if setting, well, it doesn't matter. Okay. What? Something went terribly wrong. There's no way that worked. That seems like a lot of aliasing. Yeah, I don't think that worked. Okay, that's much less aliasing. Okay, so I was right. The thing didn't work, and I don't know why. Okay. We're going to create both W and W minus I. And then when we apply W, we can bring back our do checks. When we apply W, I guess apply W minus I, we can check that, oh no, when we do A, when we apply A, we can check that applying W and then subtracting K estimated matrix is the same thing. Let's see if they are. No, they shouldn't be. So now I claim junk and out should be the same. They're clearly not. Huh. Doesn't seem all that tough, does it? Like convolving with W and then subtracting the answer should be the same as convolving with W minus I. Unless I'm using W somewhere else. Nope. Oh. Well, I was thinking maybe the fact that we're doing a two-dimensional convolution and then summing, maybe that has something to do with it. Maybe it does, but I don't see it just yet. I feel like the stream is making it obvious. I spend most of my time, I spend less than 1% of time implementing stuff. I spend greater than 99% trying to fix what should have been easy to implement. Let's check the adjoint of W minus I. Oh, it looks like I just did. Yeah, okay, it passes. There's nothing to it. There's an example where the comment was incorrect. There's this point. Oh, this is it. Oh, right, okay. W coil, right. That was silly. Okay. The first two dimensions are data. The last dimension is the coil. Apply W. For each coil, we do a circular convolution with W. And then sum across the third dimension, because the fourth dimension is also coils, but each coil gets its own set of interpolation coefficients. So right now I've got just applied W. I'm a little stuck on this very simple thing that isn't super meaningful. I mean, let's do it again. I'm just resetting everything. Okay, not everything. I'm resetting recon spirit. Got a breakpoint here. If I change that to a -1, okay, if I change that to a -1 for any single coil, it's certainly the case that, I mean, that should be it. That should be all that's required. It should give me the same thing. But it doesn't. This is a bad image. And then if I do this, if I start commenting out these things, and this of course will work because this is just the code that, this is unmodified code that we had previously checked in. Right, that's a beautiful image. Okay. So clearly there's something broken in my brain. Just changing that to -1, it does not do what I think it does. Why not? Why not? Convolution is a linear operation. Yes, circular convolution is considered a linear operation. I don't know what this is going to do, but we're at least going to track it down. Okay, so W coil. I'm going to make a new apply W minus I. So I put a 1, right? I made what basically the identity matrix. No, I didn't. My coil. My coil. My I. This is where we're at. I'm bored, so I'm wanting to check my email. Not bored, but stuck. Same thing. Okay, so now I have what this identity matrix. I can do the circular convolution with W and then my I separately, and then I'll add them together. Okay. Let's get here. Theoretically, the identity matrix is the identity of the circular convolution operation. Why didn't that? Oh, because I never called it, duh. Okay. So we're just going to do it with B. We're going to test it with B, of course. B2 is equal to applied W minus I, K data, fine. So I think temp2 should be the same as in. Wow. Temp is equal to, we could just do this on the command line. And I cannot change the font size in the command line like I can in the editor window. Okay. This is a convolution kernel with zeros everywhere except in the center, which is 1. We'll call this K. And then temp is going to be a random matrix of 256 by 256. Now I'm going to circular convolution both of those together. And I'm going to take the difference of out and temp. That's numerical precision. Okay, that's what I expected. The only difference is then the sum. What is this? All zeros? Can't be right. All zeros. Yeah, look at that. Remember this? That works very well. Okay. Oh. My eye gets created here. But applied W gets applied way up here. Well, how did this ever work? W are all zeros at this point. How did this ever work? Can anyone explain that to me? We can't call apply W until after W is created. That's a good reason to set this as late as possible. Now this should crash. Because W is undefined. How did this work? I am rather confused. The checks of the adjoints passed. When we were setting B, there's got, okay. W minus I. That's a beautiful looking image. Does it work better now? Let's undersample more. See what happens. That is with significantly more undersampling. This is only 30% of the data here. It does work better. So we just solved a significant issue. Okay. I guess we need to check that in, don't we? Sample mask gets used in apply A. Is that where it was created before? Yeah. Okay. I have no idea how it worked before. Fixed a major bug in where B was getting set incorrectly. Okay. Now I'm going to set this to -1. The only code I'm going to change, well, okay. I'm going to do it the way I've been doing it. Okay. Now I've got W minus I, right? I'm thinking that B and B2 should be the same. Doesn't even run. Oh. That's, well, doesn't matter. They're not at all the same. Okay, and so what did I do before we found this major code and major bug in our code? Feels like this should work. Why doesn't that work? Oh. Because I'm extending the size of W coil here. So if I did this, that should work. So W coil 0.2 remove index is currently 0. And if we step, then it becomes -1. Temp2 is equal to circ com2. Okay, so when I get here, I claim that the difference between temp2 and temp minus in should be negligible. I thought we did this a minute ago. Okay, going back. My I is equal to 0's size W coil. My I at 0.2 remove index is equal to 1. Conv my I is equal to Oh. right, I forgot to actually. Forgot to actually store it. Okay, this should be the same as this. And it's not. But we already saw what is convolution? It really is shifting this, is flipping the second one. Oh, an equivalent definition is flipping the first. Okay. So it shouldn't matter. Okay. Okay. This, I claim, should be the same as ASTF. And it is. My I isn't actually the identity matrix, I don't think. Like it's got too many zeros in it. For example, the zeros. No. Forget what I just said. Okay. This is actually good. Like, okay, something makes sense. Here's what I'm thinking. We're doing a two-dimensional convolution, but the kernel is that. What does that even mean to do a two-dimensional convolution like that? Oh, I'm doing them independently across slices. So it's only the identity in the first slice with my I. Right. In the other slices, my I is totally zero, and we're doing circular convolution independently on each slice. That's what I set cert com2 up to do. That's perfectly reasonable. That's what I wanted. But then subtracting there one there seems pretty weird. So we're just not going to do it. Okay. This brings us back to what we were talking about before. Where we were going to let the collected data values change. And I was saying the issue is that apply A needs to change now. Why? Because we're now changing this to over K. Subject to K minus D K minus K collected less than or equal to epsilon. And so apply A right now is doing this zero filling operation. So what to do? I think the thing to do is this. I'm going to add an epsilon like we did before. I'm going to create a new function. This is going to be epsilon 0 . if epsilon, if numL epsilon is equal to 0 or epsilon is equal to 0, then that else image is equal to non-zero. Okay. I think we find the interpolation coefficients the same. All right, I think that code is going to be common to both. This applied W, though, defining here. Yeah, okay, let's see if that works. I think it will. And I was totally wrong. N coils is undefined here. Why? Okay, we're still doing this profiler stuff, and we're not worried about making things super fast right now. We're just worried about making things work. This doesn't use the size of the ACR at all, okay? It doesn't use W size at all. Why would it? Because W size gets passed in. Okay. Great. Now, the big difference a major difference is going to be that we are going to use FISTA instead of SPIRiT, instead of LSQR. so I don't have to find the step size myself, which is, never reliable. I'm going to use Vista with line search, which is just an amazing technology. Okay, so here's going to be K star. We'll store the objective values. Why not? This is K naught. I guess in order to do this, in order to store the objective values, we need to pass in H. So Vista minimizes problems f of x plus g of x, where so you should say g of x plus h of x, where g is differentiable and h has a simple proximal operator. That's what Vista does. So what are the functions that we're going to minimize? Well, we're minimizing this. Equivalently, we can minimize that, right? Minimizing one is the same as minimizing the other. And then we can always multiply by a scalar, so we can also just multiply by a half. So that's G. Does apply W also use, do any masking or anything? No. So we don't even need W in the code. Apply W is also going to be uniform, or the same to both codes. So I'll pass in apply W here. Apply W is a function handle. We can just call it. There's a bug on line 161. Oh, of course there is. Let's see if that still works. No. Too many input arguments. M is undefined. Genuinely have no idea how SPIRiT was working yesterday. There was such a big bug in there. Okay, this is still working. Good. So now G is out equals 0.5 times the norm applied W to N minus N squared. Now, why do we multiply by this half here? Well, we're going to take the gradient of this. So we're going to take, the derivative of ax squared is 2 times A transpose ax. If I multiply by a half on the left, then I don't have the scaling by 2 on the right. That's why I did that. G grad in So what is the gradient of W minus I? Okay, so here's what we're going to do. 1/2 W minus I x. This is equal to 1/2 x transpose W minus I transpose W minus I x. I just said what the answer was. Okay. So the out is going to equal W minus I transpose times W minus I x. And so this is going to be out is equal to, I'll do this part first. Apply W to in minus in. So let's call that temp. And out is equal to apply W to in transp minus, or to temp, sorry, minus temp. Can I simplify this? So this is equal to W minus I transpose times WX minus X. This is equal to W transpose minus I times WX minus X. And this is equal to W transpose WX minus WX minus WX plus X. So that's just minus 2WX there. Wait a second. Minus W transpose X minus WX plus X. I don't see how to make this any better. Okay. K naught. So we'll just put K data in as K naught. That's the simplest thing we can do. Like this is the fewest, so we can't output the objective values like that. So then we need the proximal operator of H. Well, what is H? H is going to need a sample mask. wonder if I need the absolute value, if I could just say not equal to 0. This is doing a whole bunch of complex comparisons. But taking the absolute values, you know, a whole bunch of sums of squares and maybe an endless square root. So this is going to be a ton better. Okay, where's sample mask before? Let's just make sure it still works. All right, still works. You know, since it worked even though it was broken by undersampling by 1/2 before, let's do undersampling by 2/3. And then make sure that still works. This seems to be a more robust test. All right, good. There it is. So H means norm of in for sample mask equals 1. I wonder if I could just do sample mask. We'll do 1 for now. Minus K collected out is equal to, and if that's less than or equal to epsilon, which of course is the big difference here, epsilon. We need to supply that. We've got applied W up here. Let's check apply W there then. We'll only check the alternative A here. I don't know if we're going to have an A for this one. K collected is equal to K data, or sample mask is equal to 1. Oh, okay. Work-lib indicator function. Indicator. I'll put 0 if all the elements are within S and infinity. Otherwise, S is a two-element array specifying the interval for the indicator function. If a single-sided bound is desired, set S with infinity. Okay. So out is equal to indicator function that value is between 0 and epsilon. What do we call this? Let's call it slack. So if slack is positive, well, if slack would actually be like epsilon minus that. Like the estimated difference? The difference between the estimate and the collected? Difference estimate, sure. Okay. Now we need the proximal operator for that. Vista with line search. This is again from the DeWork library. Where does it calculate the objective values? Okay, good. It calculates them after the proximal operator. The proximal operator is going to ensure this bound is satisfied. So that's good. Okay. So I think, let's see if DeWork lib project onto ball. I forget what the proximal operator is. I forget whether I want H to be the norm, a bound on the norm, or the norm squared. So I've been storing notes. I have a bunch of notes. Proximal operators. Okay. LP norm. A whole bunch of group penalty stuff. I think this is what my student Alex did. I'm going to recon SPIRiT. Project the ball. Okay, so there's I think it looks like Alex, norm indicator of X. Norm indicator. He created a function called norm indicator. So the norm. Okay, not the norm squared, but the norm. So then this seems to be what we're doing. So I'm going to take X minus T. That's right. I need the... because I'm not taking the proximal operator of the function h, but of a scalar t times h. Okay. And so I guess we're going to do this. I need to know the dual norm for the L2 norm. And I think the dual norm of the L2 norm is the L2 norm. Do I have notes on the dual norm? I would have thought, oh, dual norm, there you go. The dual norm of the L2 norm is the L2 norm. Good. Okay, so then that brings us back up to here. So this is the answer. We're going to take this sample mask is the issue. But that just means we're only going to project those values that are in the sample mask. Okay, so out equals in, sample mask equals 1. If we could actually just use sample mask instead of sample mask equal 1, that would be convenient there. Times T times project onto ball. In sample mask equal 1. Oh. Out is equal to in. Out sample mask equals 1 equals in sample minus, divided by T. Projection onto the unit ball. The unit ball. But what about a non-unit ball for the dual norm? So that's the problem. Oh. Oh. H is not a norm, but an indicator function. What is the proximal operator of an indicator function? It's projection onto the set. A simple example is this. Non-negative orthant. Okay. So I think I'm a little confused. So where's this prox h? Here. I'm a little confused by that. Here's what I think the answer should be. Out equals in, out sample mask equals 1 equals project onto the ball in sample mask equals 1, radius epsilon, and the L2 norm. If n argument is less than 3, then P is 2. Great. I think that's the answer. T is not used, and that makes sense. T is not used with a projection, but we're still going to keep it as an argument because FISTA assumes you're supplying a function prox th that accepts 2 arguments, where the second argument is the scaling parameter. K star here without running anything. Like I don't know what else I need to do at this point. I just need to run this and debug. Let's see if it even runs. I have a meeting in 20 minutes. Set timer to 10 minutes.
10 minutes starting now.
Thank you, Siri. Prox th out equals in. Why did that crash? Not enough input arguments? Prox th. Oh. This happens when you forget to put an at symbol when you call it. I could just use fro here. And I think that's the same thing. This means take the Frobenius norm, which is like taking the Frobenius norm of an ND array is just taking the sum of the value element value squared and then square root, which is the same thing as turning that into a vector, and then taking the L2 norm, which is what I would have had to do. Okay. This seems to be running. The objective is infinity, though. Let's see why that is. let's see, the line that's coming out is Vista with line search. Objective values. Well, I started out small. Calculate objective values. So what is h of x? Is that infinity? How can it be if we just project it? This is the gradient descent update. So x, I believe, oh, because I'm not projecting this onto epsilon, I'm projecting that minus k collected onto epsilon. One bug down, 5 to go. Thank you, MATLAB. Where does the objective values get set again? Here. Now is it infinity? Yes. How can that be if I just project it? Okay, so this is like the new x, then I do a projection. Where's gx get used other than there? Oh, for the line search, okay. Project on the ball. One 179040. Some 179040, okay. And what size is in here? Okay. Epsilon is 1. This is going to project onto the ball. And that means that this should be less than or equal to epsilon. Am I going bonkers? Does projecting onto a ball not project onto a ball? The norm is 18. R is 1. What's the norm of out now? 1. Good. So what's the norm of... Oh! Okay. Plus K collected. And now the objective is not infinity. Seems to be going down. Oh no, the objective got to infinity. It should never do that. Might have been due to numerical imprecision. Okay. Okay. Looks like it works. So now we can handle non-zero epsilons or zero epsilons. The zero epsilon uses LSQR, more efficient than FISTA, but FISTA is fine. I didn't check in that for the fix to that comment. Okay. K collected. Let's replace that with K collected. Everywhere. K estimated, let's replace that with K estimated. Everywhere. Okay. Okay. Just checking this code. Thank you, MATLAB. My recon SPIRiT can now accommodate non-zero epsilon. Status diff run recon SPIRiT. We're going to leave that for a long time. Well, we don't need to check that. Oh, I guess git add run recon SPIRiT git commit made test more difficult by undersampling more. There you go. solved a huge bug that's insane that it ever existed. And we accommodated non-zero epsilon. See you guys later.